I have worked on many different areas because I'm easily distracted by something new and shiny and different. So while Uri was trying to break the wall by hitting into the same space for 10 years, I was just trying to poke at the different spots and see where it's moving and where it's not. The main goal is to basically investigate and understand the properties of quantum space. And we have to admit that we are not even sure it exists. Like maybe gravity is different to other forces of nature and it's not quantum. We have to be open to this possibility. Maybe gravity can be quantum, but in a way that I'm not going to be describing next minute. So maybe it's completely different to what we are assuming, and we should be comfortable in this setting. Like we don't know if this is the correct approach or not, because this is how science works. We have to try something, and if it's not working, try something else, and then something else, and so on. So this will be one effort to glue together a narrative about how to think about quantum space from some fundamental definitions up to something maybe observable and testable. So again, now I'm going to be repeating both after myself and Uri 2 times. So some of the slides are like the expressions are the 4th time here on the blackboard today, but this is what it is. The main point is that we should be expecting some changes in the mathematical description. So it's very difficult just to take Einstein's theory of gravity, the way he knew it, and modify it slightly and make it quantum this way. We should be probably expecting some kind of modifications, expressing things differently, and then gluing them together with the quantum theory. So we should be open to new ideas, and on the other hand, we shouldn't be maybe hoping only for mathematics to do the heavy lifting. Because so far, a huge part of this community has gone so deep into the mathematical structures of different values of quantum gravity. We spent a lot of time investigating something. We don't know actually if it really exists in a physical sense of the word. So I'm sometimes happy not to be completely mathematically accurate. If this is just a guess how the universe or the nature works, and if this guess turns out to be correct, then we can redo the math and see how to glue everything together. And this is how physics worked so far. People discovered something, it made loose assumptions, and it was sort of working, and then brushed off the mathematical details. So the outline of this part of the lecture will be threefold. First will be the modifications of quantum mechanics. So we take quantum mechanics, we modify something, then realize we have to modify way more than naively we're expecting, and then see how this new theory leads to some observational effects or lack of. Then I will have a little detour into matrix models because they are very popular for studying new type of theories, not only like in M-theoretical setting or string theoretical setting or quantum gravity setting, but they were studied in nuclear physics and so on. So quite fruitful models. And then I'll again dig a little into phenomenology just to end somewhere. Okay, so let me start with quantum mechanics. I'm assuming everyone knows quantum mechanics, at least in the context that it's different from classical mechanics of Newton, etc. In Newton's physics, you have momenta, you have positions of particles, and everything can be measured with arbitrary precision. In quantum mechanics, we know this is not true anymore because you cannot measure position and velocity at the same time, because if you increase the position measurements, you decrease what you know about the momentum and so on. And again, you cannot just do Newtonian physics, add a new fourth term to your equations, and now suddenly it's quantum mechanics. Entire formalism had to be changed to incorporate those new effects, which are fundamental on the deeper level. So it's something that I said in the previous lecture, that we started with mathematics that are very known from everyday life and intuitive. And as we are going deeper and deeper and deeper, we are observing new type of structures, trying to understand them, investigate them, and hopefully not losing track with something we can know intuitively, but sometimes this can be the case. Okay, so now we want to have a quantum mechanics that is twice non-commutative. First non-commutativity is in the phase space, which means you cannot measure position and momentum at the same time. Now we don't want to be able to measure even position itself with arbitrary precision. There are many ways how to postulate the right side of this equation. This is one of them, which has some nice properties, which has some less nice properties, but this is something that was starting point also for us. So we chose to study quantum mechanics modified by non-zero side for this non-commutative relation with a particular right-hand side. This has been studied before in different contexts. We, and by we I'm meaning me with Peter, left a couple of minutes ago, and Veronika Galikova, studied one particular mathematical formulation of this theory, which is formulated using two sets of auxiliary operators, which might be known from the study of harmonic oscillator ordinary quantum mechanics. So we have two sets of operators that create and annihilate in an auxiliary Fock space, and we can use those to borrow or to inherit the non-commutativity because their ordering matters. So we can use them to define a position operator which won't be commuting with itself depending on the coordinates. So this has been assumed. We can use those operators for our construction to produce non-commutative coordinates, and then to do physics. Here I used scalar field theory as an example of physics. In quantum mechanics, you can start with the Hamiltonian. So this is the free Hamiltonian, which can be derived in a sense to look like this. So we have physical states expressed in terms of coordinates, which has been defined this way, and we have the kinetic part of the Hamiltonian defined likewise.
There is an index alpha saturated in the definition of xi, no?
Yes, yes.
Yeah.
I was too lazy for that. Yes. So here are two, whoops. These are two of them, and yeah. Okay, so the first study we did was about the velocity operator, which is one of the most important objects. You want to know the Hamiltonian, some sort of notion of coordinates, angular momentum if you want to rotate stuff, and then the velocity operator or the momentum operator. So we defined it using the Heisenberg relation, Ehrenfest relation, and then studied its properties. So on some level, it well behaves. So it's rotating as a vector, it's commuting with itself. Now there are some deviations from standard relations. So for example, the relation between the square of velocity and kinetic energy is modified, which is a very important feature of the model. And also the uncertainty relation is modified. So if the energy is very small, this is small and this is small, you can ignore this. But if the energy is very large, you can see some deviations from it. And as we started working on this, we noticed that squares of some operators sum up to constants. So for example, you can define a new operator, which is basically a modification of the kinetic energy, and it forms a sort of a S3 structure with the rest of the velocity operators. Overlooked equation from the paper, which is, 12 years old, is the relation for the acceleration operator. As I was putting together the presentation, I just refreshed my memory about this, so we can compute what is the expected acceleration of a particle. You can see the ordinary term, the gradient of the potential, and then there are some corrections. This can be set to 0. This is the angular momentum operator. This is the Laplace-Runge-Lenz vector. But here we can see something which is again very small, proportional to the second derivative of the potential term. So maybe this term warrants a detailed investigation and to see if it can form the sort of outward pressure or some sort of drag, or how is it affecting the particles. So some of the structures have been studied directly from the velocity operator definition. Some were defined and overlooked for 12 years. So hopefully next couple of months we can have a look if those can be insightful in any regard. Now, the previous started actually, this started as my diploma thesis and then was developed into a paper with Peter. And then I started doing PhD here, and I didn't know PhD students are expected to work during the summer. So I didn't. And I came in September and noticed that Peter and Veronica are working on something called Laplace-Runge-Lenz vector. Before that, they studied the Coulomb problem and showed that you can actually, within this modified theory of non-commutative quantum mechanics, you can derive the energy spectrum exactly. This is nice because in many theories of quantum space, you can do perturbative studies, but not exact results. So the hunch was that some symmetries have been preserved by the construction, and you can squeeze the result from the symmetries themselves. The symmetries of the hydrogen atom problem are described by this vector. So you have the angular momentum vector, you have the conserved energy, and then you add this vector called Laplace-Runge-Lenz, and this discovered by Hermann and someone else, so completely mismatched with the names. So you can define it like this. And all together have an algebraic structure that can be used to derive the energy spectrum, so it can be solved without solving the Schrödinger equations. So they were working on this. So I wanted to hop on the train, which was already moving. So I decided I will try to do it myself in a different way, which proved out to be a good idea because, again, I'm mildly lazy. And I noticed that I'm doing the same calculations multiple times while calculating different combinations of the operators. So I asked myself if I can split those fundamental objects into smaller parts and then see how those are interacting together. So take the model, split it into smaller parts, and then see how they can fit together. So then I basically redone their calculations using different operators and different physical objects, which was interesting because we started noticing a different symmetrical structure, which we utilized later in the study of magnetic monopoles. This is interesting aspect of Peter. He just starts giving you papers which has no connections with what you are doing right now. And then maybe in a year or two, you'll start realizing, aha, he saw that this is coming and wanted to prepare me. So when I was his extremely confused graduate student, started trying to figure out some properties of velocity operator, he started giving me papers about magnetic monopoles, and I was like, okay, maybe he just wants to show off or something. And then actually, after we noticed that those operators can be split into smaller parts and started to glue them together again, we started noticing relations that are known from the theories of magnetic monopoles. Magnetic monopoles are hypothetical particles that are sources of magnetic fields. I want to say that we know they don't exist, but I would say we haven't observed them more than once. This is called the Valentin monopole, observed on the 14th of February 1982 or 84, something like this. So there was one beep of the detector trying to find magnetic monopoles. The current view is that they might have been formed during the earliest stages of the universe, but then later where their concentrations has been diluted by the process of accelerated universe. So they are present in the universe. They are very rare. They are probably very massive, so it's difficult to make them in colliders, but you can make condensed matter act as a magnetic monopole. So it's not magnetic monopole itself, but it's organized movement of different particles acting as a magnetic monopole. So we can sort of create them in a lab, but in a different way. And it would be nice if they existed, because they can be used to explain the quantization of electric charge. We know that electric charge appears only in different values in the universe. And this can be explained if there are also magnetic monopoles, and there's some combinations forces you to make their product quantized, and that means each component is quantized as well. So people paid a lot of attention into studying magnetic monopoles, derived plenty of equations. So for example, if you have commutators of momenta, they have this right-hand side that looks like Coulomb potential with a coupling constant that is combination of electric and magnetic charge. And the states, as we have been studying them so far, had same number of creation and annihilation operators. This is because, again, lazy notation, for each creation operator there is a single annihilation operator. So no matter what type of function you choose as a function of this x, it will contain same number of creation and annihilation operators. So then what we tried is we added one more, two more, three more, either creation or annihilation operator, and see how the equations changed. And they changed rather drastically. For example, the commutator of velocity operators is no longer zero. It produces this non-zero side. So there is I, the imaginary unit. There is kappa is the difference between the number of creation and annihilation operator. And then there is something that resembles this Coulomb term. And we actually re-derived in this theory many different properties of magnetic monopoles just by considering states of non-zero kappa, meaning have mismatch between the number of creation and annihilation operators. Interesting thing is we are motivated by the drive to understand noncommutative quantum mechanics, but this can be rephrased completely in ordinary quantum mechanics. So the first step is to rephrase ordinary quantum mechanics in a different language, then do modification of this type, and then by considering generalized states, you have different descriptions of magnetic monopoles. Usually you can describe them, for example, by having a potential which is singular on a line or a half line, so-called Dirac string. But now, using the description we developed here, you can just use a different formalism and describe them in a very neat way. Okay. Matrix models. Now, here I made a huge introduction into this, so I can be slightly briefer. The main idea is that in some cases, the dynamical content of physical theory can be described using a matrix or matrices of certain size, of certain structure, of certain properties. One of the simplest examples is the fuzzy sphere, which is basically a field living on a sphere which has some kind of quantum structure described in terms of matrix harmonics or some kind of basis for matrices. So you are using Hermitian matrices to describe functions living on a sphere with limited spatial resolution. This is known. Again, you can do physics. Now, physics in the sense you can define scalar field theory and try to understand its properties. And doing physics means computing the mean value of observables. So some of the papers mentioned in my habilitation thesis is regarding matrix models. Some of them is the fuzzy spheres and models adjacent to it, and some are matrix models originating from the M theory or from this setting. This is plot similar to Uri's plot. It didn't take 10 years to produce. This was just 500 gigabytes of numerical data and a year or two to put everything together. But it's basically a simulation of a scalar field theory with quartic interactions living on a fuzzy sphere, done using hybrid Monte Carlo simulations. We try to compute the position of the triple point, which is somewhere around here. Like you can see, if your home garden was measured with this precision, it wouldn't be very helpful, but we basically narrowed it down to somewhere around here. You cannot see the digits, they're rather small. So we think we localize the triple point compared with Uri, and we agreed somehow, let's put it like this. Then after returning to Bratislava, I kept working on those models, and for example, we tried to develop a new algorithm that would help you get from configurations which seem to be stable, but are just metastable, which means that you have, for example, two wells, half of the eigenvalues are here, half are here, and they would prefer to get to the same well, but it's very difficult by just random jiggling to coordinate the movement, so we tried some different methods. So we are now able to say which phases are actually stable and which are just metastable in some, in a way. So we have been studying this a lot, and then recently it's 2 years ago, this paper, so it's published a year ago, but we were working on it a year before, is about something what we call the fuzzy onion, which is a straightforward idea, difficult to put together. So we know how to do physics on a fuzzy sphere, but who cares about a sphere if we are three-dimensional beings? So we want to have something three-dimensional. So we just put a sphere within a sphere within a sphere within a sphere within a sphere, which is a straightforward idea, difficult to put together because each of the sphere, if the scale of non-commutativity is kept the same, would be described with a matrix of a different size. So this is matrix 2 by 2, 3 by 3, 4 by 4, and so on. And it's too difficult to do physics if you are trying to glue together spaces with different number of degrees of freedom. Because, for example, we want to take derivative. Taking derivative means this minus this, and it's difficult to do 3 times 3 matrix minus 2 by 2. But then we realized that, well, you can overcome this by defining a new set of operators that takes larger matrix and squeeze it, and may take smaller matrix and expand it. And you can do this by utilizing basically this fact that we can expand the terms in sort of a basis of something that would be spherical harmonics in three-dimensional space or on a sphere. You can do the expansion using a small matrix, take the coefficients, and using the same coefficients produce a larger matrix, or the other way around. So we defined an operators that connected consecutive layers together, and with that we are ready to do physics. Again, doing physics either means doing some kind of scalar field theory or quantum mechanics. And actually in this case we have done so much more. For example, heat transfer. So something very classical, ordinary physics, and we are hoping to do, for example, I don't want to promise like Navier-Stokes equations or meteorology or plasma physics, but in principle this can be done, and we are allocating at least small percentage of mental effort towards this goal. So maybe doing ordinary physics in three-dimensional space expressed in terms of matrices. And this is a slide I added when Peter yesterday called me that he will come, but then he left, so I'll let you know anyway. When he and Veronica 12 years ago discovered or studied the hydrogen atom problem, they noticed an interesting feature. Not only they saw the ordinary set of bound states for the hydrogen atom and then a set of scattering states, they noticed a set of very high energetic bound states for a pulsive potential, which is super weird twice, because it's bound states for a pulsive potential and it has very large energy. So we studied the fuzzy onion model, and basically we took a large cavity, placed a particle in it, so it's a proton here, electron here. They are stuck in a cavity because we have finite resources, so we cannot make the matrices arbitrarily large. And then we saw how the solutions to this problem look like, what the electron is doing around the proton. Then did the same for antiproton, and in our case the number of degrees of freedom is finite, so we have a finite set of solutions. So we actually observed that for electron-proton system in a cavity you have this kind of radial probabilities, so you have some bounded states, and then you increase the energy, the particle is just moving back and forth in the cavity, then something funny happens in between, and then it again cools down and it's repulsed. And when you do the same study for negative potential, you start here, go through this transition, and then see something that actually really looks like a bounded state with very high energy and with negative potential. But finally, we had the tools to understand how this is working. So this is what we noticed. Positive potential, we have a set of solutions with energies 1, then negative potential, flipped by a mirror symmetry to have a negative sign. We have second set of solutions, and then we notice that they aren't completely arbitrary. They are connected by a matrix, which is diagonal of this form. So it's not the functions would be really the same. They are like the same function multiplied by something that is very swiftly oscillating. And you can actually prove that for this property to hold, you need to satisfy those two conditions. So first, the new matrix should be commuting with the potential. It should be anti-commutating in this way with the kinetic part of the potential of the energy. And if it does, then you have this new type of solution for this mirror potential. So it's working very nicely, and finally we understood those weird states that they have observed, but now we're trying to figure out our new weird states. You see something is happening here in between, and then you have this switch type of the spectrum. This is clumped around the proton, and this is clumped around the edge of the cavity. Okay, now very briefly in a couple of minutes. M-theory is a good source of interesting models because in some cases it has gravity dual in the sense of holonomic description. We study some models. One of them which I included in the thesis is the study of BMN model, because we have observed that this model, which contains 9 spatial matrices plus temporal direction plus supersymmetric partners, contains fuzzy spheres as part of the solutions of the model. So the model settles in a fuzzy sphere vacuum and then can hop into a different fuzzy sphere vacuum and then hop into a yet different vacuum. So it's like formation, then sort of like a formation or jumping between different fuzzy sphere configurations. So it's not completely like the emergence of space, but it's something in this regard. You have something that looks nothing like a space, and it organizes itself to form something that looks like a fuzzy sphere. And then the phenomenological aspects I've discussed also during the first part, so just a little bit more details into this. So this is the main idea. You take a regular or smeared delta function, use it as a source for the Einstein field equations, solve for it, and you can actually show that in this case there is either 0, 1, or 2 horizons. Usually there are 2. One is very close to the origin, second is very close to the Schwarzschild radius, and as the mass is decreasing, they are moving towards each other, and when they meet, it means that the G0 component is at the horizon, has 0 derivative, which means the temperature drops to 0. So again, in a very general settings, we can prove that the small black hole behavior is robust. And these are some interesting aspects I have mentioned before. Like, you can use them not maybe as a sole source of dark matter, but maybe contributing maybe 50% of it, 25% of it. To know the exact ratio, we can hope for data from the primordial black hole gravitational wave spectrum to deduce the spectral index of the primordial energy fluctuation spectrum. And then we can say something about what is the expected number of microscopic black holes and so on. But they are very good candidates, and I wouldn't be surprised if there are some flying around us. So the outlook, last minute, there are many interesting aspects. So for example, when we formulated the fuzzy onion space, we are using a matrix that has a lot of empty spaces, and it feels like they can be used to accommodate something describing sort of a string state, or at least something that is stretching between different layers. So we want to see if what we are studying in the fuzzy onion model is whether it's somehow connected to something you was studying with Harold. There are still some BMN studies that are left to be finished, but I would be eager to study more the situations when we see some sort of fuzzy sphere configurations appearing, and to see first what sort of field theory is happening on top of the fuzzy sphere, and if the two consecutive layers are interacting with each other in some way. Then we can use the fuzzy onion space to understand gravitational collapse. So for example, if formation of singularities is prevented, so we take a bunch of mass, let it collapse in an Oppenheimer way, and see if singularity forms or if it goes scatter somehow, or what would happen in this case. We have done some preliminary studies squeezing particle in the cavity and trying to see some deviations from the expected behavior of the pressure. Again, trying to see connections between what we are doing and some early cosmology models or matrix cosmology models and so on. See more if there are some other window of opportunities to test the effects of vacuum dispersion. There are new ways being discovered. I don't want to say like every week, but new paper on archive every couple of weeks, trying to understand some new kind of phenomena using quantum nature of space. Most of them are, I would say, very, very hopeful, to put it mildly, but still we have to keep searching. And this nice little detour is trying to see if we can study classical physics on the fuzzy onion space. So far we have been motivated by studying quantum structure of space. So our constant lambda is very, very small. Maybe Planck scale might be larger, but still very small. But what if we can take it actually to be very large, to be describing some sort of real world limitation of the spatial resolution? So for example, if you want to do meteorology, you don't care about nanometer physics because you have the meteorological stations, I don't know, every 50 kilometers. So if you want to do meteorology, you can basically do it on the fuzzy sphere or a fuzzy onion space when the lambda would be 50 kilometers, describing the limit not of the space itself, but of the way you can measure it, and then keeping the resolution of the model constant across your study. So this might be quite promising, and one of my students is working also on this, and maybe in a couple of months we'll see some results. So thank you for your attention.